Okay. Yeah, we had some technical issues. What a surprise, no? Okay, great. Yeah, so today, first of all, welcome everyone to lecture 13 of computer architecture. And we are live, I hope, right? Good. Professor Mutlu is traveling, so I will be teaching today. And tomorrow also, one of my colleagues, John, will also teach. So today we're gonna have two lectures. The first, I'm gonna continue memory controllers, like our discussion on service quality and performance. And then after finishing the first part, we will jump into emerging memory technologies. Actually, that's gonna be the main topic for today. But before that, I prefer to conclude our previous lecture. Any questions to start? Okay, great. So we were discussing about memory scheduling for heterogeneous systems. And this was one of the systems that we were discussing, like the current system on chip architectures. They have quite a lot of heterogeneity. You can see that we can have different CPU cores, like large CPU cores, as well as small CPU cores, GPU, hardware accelerators, DMA. And essentially, like the memory controllers here should be able to handle all these different devices with different characteristics. And applications that they are running on all these different cores and different processing elements, they have different characteristics. Could you please also close the door? Thank you. So yeah, so we wanted to see how to allocate resources to heterogeneous agents to mitigate interference and provide predictable performance. I'm not gonna go into detail about all of this again. I'm just gonna flash some of the slides that we showed. So essentially, if you want to learn more about heterogeneous systems scheduling, you can watch this lecture from Professor Mutlu. And in general, if you want to learn about heterogeneous computing system, you can check this lecture, even though we're gonna also have this kind of lecture in this semester as well. But if you are kind of impatient, you can go ahead and watch it. But essentially, we have done a lot of work in this domain, and we designed different memory scheduling techniques. Stage memory scheduling is one of them, that it provides quite good performance in CPU, GPU integrated systems. And I mentioned also previously, long time ago, I guess in lecture 2 or so, that GPUs usually they are throughput oriented, and applications that they are running on GPU, they issue a lot of memory accesses. And at the same time, these are kind of error tolerable. So for GPU applications or for GPU in general, it's mostly important that you provide quite good bandwidths to access memory. But for the latency, as long as DRAM access latency is on their, some tolerable region, you can hide it, but using scheduling threads, basically. But for CPU, actually, applications are quite latency sensitive most of the time. So dealing with these two is quite challenging, and this work actually look into it. We have done also more work on this area. This work you can also take a look. Also about other topics like handling CPU and IO interference, like decoupled direct memory access, like we isolate CPU and IO traffic by leveraging a dual data port DRAM. As I said, I'm not gonna go into detail of this. But then we also jump into predictable performance, like how we can have strong memory service guarantees. Again, we get back to this example that we want to have basically allocate resources to these heterogeneous agents to mitigate interference and provide predictable performance. If you want to learn more about predictable performance, you can go ahead and also watch this lecture from Professor Mutlu. Yeah, and these are some papers that I'm gonna also cover some of them a little bit later, like by doing source throttling, that essentially you think that you consider that your resources are dumb. They don't really do intelligent scheduling or whatever, but you can try to throttle from the source, to reduce. In my example, for example, GPU and CPU, One option, when you see that, okay, CPU threads are getting like degraded, like they perform because they cannot get enough scheduling slot. One way is just to ask GPU to send less number of requests. So you can just throttle GPU threads to not send too many requests. So that's an example of throttling, for example. And that can be useful to avoid interference and provide predictable performance in many cases. Yeah, as I said, we also continue in this direction, and we have published quite a lot of different works. And yeah, but I want to basically look into QoS approaches a little bit more detail. So remember that fundamental interference control techniques that we discussed, like the goal is to reduce and control inter-thread memory interference. And we can do prioritization or request scheduling, also data mapping to banks, channels, ranks, core source throttling, and application thread scheduling. I like to, touch upon these three techniques, 2, 3, and 4 here. Again, if you want to learn more about QoS techniques, you can also watch this lecture from past. And memory channel partitioning that you're gonna see actually is one of the techniques. So this work, I'm gonna discuss a little bit about how memory channel partitioning can help. Like in this example, consider that we have two applications, red application and blue. And if you have two channels to access memory, so one case could be, all requests are scattered across two channels. So in channel 0, you have to service requests from red application and as well as blue applications. So this basically this can cause interference between applications requests, right? So one way to handle it is to do channel partitioning. So basically you send all the requests from red application to channel 0 and all requests from blue application, for example, to channel 1. And this can eliminate interference between applications requests. So yeah, so in memory channel partition, our goal is to eliminate harmful interference between applications. And the basic idea is that map data of badly interfering applications to different channels. So essentially, it also involves data mapping, like the application data mapping in this domain. So there are some key principles that you should consider here. We need to separate low and high memory intensity applications. And also we need to separate low and high row buffer locality applications. I will show some example about them later. So in key insight 1 that we want to separate by memory intensity, like high memory intensity application interfere with low memory intensity application in shared memory channels. So you can see here that for red applications, we have requests to different banks. And red application actually issue a lot of requests. At the same time, blue application has only a few requests, but since we don't really partition them, like we don't have any channel partitioning, blue application request needs to wait for red application, and that's not good. So in a better way of channel partitioning, you can actually, if you have all the requests from application red to channel 0, you can essentially address all of them like this. And then requests for blue application can go only to channel 1. And you can see that you can save a lot of cycles for blue application. And you can also save cycle for red application at the same time. So in general, it causes better performance. So map data of low and high memory intensity applications to different channels is one way to, provide better predictable performance and quality of service. Another insight that we like to focus here is that separate by row buffer locality. Sometimes there are applications that they have high row buffer locality that they basically you can address requests from low buffer, so you don't need to close the row buffer pre-charge by doing pre-charge and activate another row. But there are some other applications that they have poor low buffer locality. So if you actually mix these two applications to the same channel or to the same bank, it's going to be mess basically, right? So it's so clear that essentially if you partition these two applications nicely, like you can see that red applications, here you have quite good row buffer locality, but for blue applications, you don't. So yeah, so essentially for blue requests, you need to wait more because you have channel, you don't have a low buffer locality, but at the same time, you don't need to wait that much for red applications, and you can benefit from quite good row buffer locality that it has. However, there is one issue here. Basically, so you need to profile applications, of course. You need to classify applications into groups and partition channels between application groups. And after partitioning, you can assign a preferred channel to each application and then allocate application pages to preferred channel. So what we do profiling applications at hardware, and all the other steps are system software. They need to be handled at the OS, basically. So if you look at the time for the first current interval, you do profile applications. And then after finishing that, you need to do other steps like classifying, partitioning, and assigning. And then you can do the next interval like enforcing channel preferences. And you can benefit. However, there are some observations that we want to discuss now because these can actually enable some other optimizations. So applications with very low memory intensity rarely access memory. So when we do this channel partitioning, we don't want to have one channel with quite high utilization and another channel with quite low utilization. So that's not good, right? So dedicating channels to them results in precious memory bandwidth waste, which is not good. They have the most potential to keep their core busy. So these applications that they have low memory intensity, probably they are also quite compute intensive. So they can actually, they can be scheduled on CPU cores, and they can keep the core busy, for a long time. So it might be a good idea, just, I don't know why animations are going on their own, but yeah, maybe these slides also have some automatic animations, I don't know. Anyway, yeah, so they can have most potential to keep their core busy, and they interfere minimally with other applications. Essentially, prioritizing them does not hurt others. So if you prioritize these applications with low memory intensity, they don't interfere with other applications, because they don't have a lot of memory accesses. And at the same time, if you prioritize them, they're gonna keep core busy, which is good. So we'd like to keep all the elements in our system busy. So this is a good observation. So that brings us to this new technique, which is integrated memory partitioning and scheduling. So you do partitioning, but at the same time, you also do scheduling. So you do these two techniques together. So we always prioritize very low memory intensity applications in the memory scheduler. That's part of the scheduling. But at the same time, we also do channel partitioning to mitigate interference between other applications. So here are also some results for hardware costs, like memory channel partitioning. We do profiling in hardware, so we need some counters. We don't need the modifications to memory scheduling logic for memory channel partitioning, and we also have some storage cost per number of cores that we use. For the integrated memory partitioning and scheduling technique that we do scheduling, so at the you also need to do scheduling. So there are some logic that you need to implement, and that's a single bit per request essentially. Now let's take a very quick look at some results. You can see that all results are normalized to FRFCFS, and all these techniques like MCP and IMPS, they actually provide better performance compared to state of the art back then. So better system performance than the best previous scheduling at that time at lower hardware cost. And always we need to avoid bad channel partitioning. This is a very good example in Swiss airport that you can see how poor channel partitioning can make long waiting for everyone. So it's very important that we use this analogy also to when we are designing computer architecture and essentially computer systems. So combining multiple interference control technique is a good idea. Now you see that we had this memory partitioning technique, like channel partitioning, sorry. And that provides some performance, but at the same time, we observe that while we combine it with scheduling technique, you can actually make much better performance. So it's always good to think about combining different ideas or techniques such that you can hopefully combine the good capability of them. But there are some key challenges, of course, like deciding what technique to apply when, or partitioning work appropriately between software and hardware. And of course, there are upsides and downsides. So at upside, like the MCP and IMPS, so we can keep the memory scheduling hardware simple. We combine multiple interference reduction techniques, and that can provide performance isolation across application mapped to different channels. And so general idea of partitioning can be extended to a smaller granularity as well in the memory hierarchy. It doesn't need to be at that channel partition. It can be across banks or subarrays or etc. But there are some downsides, of course, like reacting is difficult because we do profiling and then we make a decision for the next interval. So you always need to basically should consider that reacting is not that fast. So sometimes you cannot really react to workload changes that happen frequently. And the overhead of moving pages between channels that can restrict benefits. Sometimes when you want to obey some channel partitioning, so you need to move some data from one channel to another channel. That can cause actually memory data movement, which we don't like it either, right? So these overheads you should always consider, and they can essentially restrict the benefit of this technique. If you want to learn more, you can actually check this paper. But let's also talk a little bit about source throttling. How we can, any questions? Am I going too fast? Okay. I wanted to finish the first lecture in 30 minutes, but let's see. I mean, 30 minutes from the time that we were supposed to start. Okay, so source throttling, the key idea is that we want to manage inter-thread interference at the cores, like sources, not at the shared resources. So we dynamically estimate unfairness in the memory system and feedback this information into a controller. And then we can throttle cores memory access rates accordingly. Like back to my example, you can, for example, ask GPU to throttle GPU threads, to not send memory requests, basically. What that means? That means that, very simple implementation, you can just install those threads, right? But there are also other ways to do that. For example, we have this MSHR for cache, L1 cache. You can, for example, try to limit the number of outstanding requests, right, in MSHR. So that can essentially reduce how aggressively you access memory. So if unfairness is greater than system software specified target, so there should be some threshold here. We throttle down core causing unfairness, and throttle up core that was unfairly treated, essentially. You can, of course, check this paper to learn more about it. But there are two components here. So we have this runtime unfairness evaluation in hardware. There should be some mechanism to understand that, do we have unfairness or not, basically. And it needs to dynamically estimate the unfairness by, for example, calculating application slowdowns in the memory system. And then estimates which application is slowing down which other. And after that, there is the second component of this technique that we do this dynamic request throttling. And with that, you can adjust how aggressively each core makes requests to the shared resources. And by throttling down requests, you can basically avoid some unfairness that you already have. For example, you can limit miss buffers, like this MSHR, or limit injection rate of that MSHR table. So yeah, so this fairness via source throttling, this is the paper also in AS Plus 2010. We have different intervals. In the runtime, you can do this runtime unfairness evaluation. And in first interval, we do a slowdown estimation. And we find application with the highest slowdown and find application causing most interference for application, like the app is slowest, like the application that has the highest slowdown. And we call that application as an app interfering, basically. And now that we have this unfairness estimation and we know which application is the slowest one and which application is the interfering one, we can enter the dynamic request throttling. And essentially, you can throttle down app interfering and throttle up app slowest, basically. So let's see how we can do this dynamic request throttling. We can adjust how aggressively each core makes requests to the shared memory system. For the mechanism, we can use this MSHR, like the quota, that controls the number of concurrent requests accessing shared resources from each application. We can also request injection. Basically, we can tune the request injection frequency that controls how often memory requests are issued to the last level cache from the MSHR, right? So here you can see an example like this throttling level that assigned to each core. And for example, when throttling level is around 10%, your MSHR quota is 12, and your injection rate is also once every 10 cycles. So by controlling this throttling level, and when throttling level is 100%, meaning that you don't throttle at all. So it's the other way around. And when it is 2%, so you are actually throttle that thread or that application a lot. Fairness objectives can be configured by system software, keep maximum slowdown in check. We can consider that estimated max slowdown should be lower than target max slowdown. So that's one way of doing that. Or we can consider that a slowdown of particular applications in check to achieve a particular performance target. Like estimated slowdown of application I should be basically lower than targeted slowdown. So there might be some applications that quality of service for them is important for you, so you can consider them in your fairness objective. Sometimes all applications are the same. I mean, you can treat them the same, so you can consider the max slowdown and just try to consider that as a fairness technique. There can be other techniques as well. And the support for thread priorities, we need basically this weighted slowdown that you calculate. Yeah, so if you also want to take into account thread priorities, you can do weighted slowdown. So each slowdown can be time to the weight of that. So with that technique, you can also consider that, you know, if you have different applications with different priorities, probably this metric can be more useful for you. Yes. So my short answer is that I don't remember, but nothing, in my opinion, that it can be actually quite, you can actually go fine grain even more also. I don't see any reason that you cannot, for example, like, yeah, for example, you can consider that, okay, I'm gonna define throttling level of, I don't know, 20%, and MSHR quota is gonna be, I don't know, 20. You know, you can just come up with something. And there might be, I think these might be some examples, but that being said, I also don't remember what was the exact mechanism. But fundamentally, I think doesn't need to be only these throttling levels. Okay. So let's conclude with some takeaways about source throttling. Source throttling alone provides better performance than a combination of smart memory scheduling and fair caching. This is good. And neither source throttling alone nor smart resources. When we talk about the smart resources, we consider this like scheduling technique, you know, that your resources also try to, once you have a shared resource, you're gonna also try to schedule that resource in a smart way such that you can avoid interference. So neither source throttling alone nor smart resources alone provide the best performance. So as we discussed, also combined approaches are even more powerful. And we observed that actually in our previous example that we combine memory channel partitioning with memory scheduling, that we provide better performance. So let's also discuss about some ups and downs in source throttling. As a good thing is that core and request throttling is easy to implement, and no need to change the memory scheduling algorithm. These are really good, and can be a general way of handling shared resource contention. And it can reduce overall load contention in the memory system. So you just lower down the volume of that thread or application, and the whole system can be free for some time, basically. And other threads or other application can breathe, for example. But of course, there are some disadvantages, like it requires slow down estimations. It's difficult to estimate, and sometimes it's not, of course, it's not also accurate, to estimate. And thresholds can become difficult to optimize. So how do you tune your threshold, essentially? And it can cause throughput loss due to too much throttling, for example. And it can be difficult to find an overall good configuration, of course, in doing source throttling. Makes sense, right? Okay, so if you want to learn more, you can check this paper. We have done more work also on source throttling. I'm going to flash some papers. You can check them later if you are interested. They're going to be also part of your reading in homework 3, I guess. Yeah, so also in on-chip networks, we can do this source throttling. And these other works. But now let's summarize this lecture. So the goal, as you remember, was to reduce and control interference. We discussed different ways to do that, like by prioritization or request scheduling, data mapping to banks, channel ranks, core and source throttling, application thread scheduling. And of course, best is to combine all. And we discussed how we can do that in some examples. And approaches that we discussed, like smart versus dumb resources. Like a smart resources approach could be like QoS aware memory scheduling. But for dumb resources, we also discuss approaches like source throttling, channel partitioning, for example. And we also discuss how both approaches are effective at reducing interference. And there is no single best approach for all workloads. So in the end, combination of them makes sense. And we design some techniques based on these, like request thread scheduling, source throttling, and memory partitioning. And we show that all approaches are effective at reducing interference and can be applied at different levels, hardware versus software. And there's no single best technique for all workloads. And at the same time, we discussed that combination of them provide quite good performance. So when you have a QoS on aware memory, you have uncontrollable and unpredictable system. That's why providing QoS awareness improve performance and predictability, fairness, and utilization of the memory system. And we discussed many new techniques to minimize memory interference, provide predictable performance, and many new research ideas needed to integrate these techniques. We didn't have time to discuss or cover a lot of other techniques. You can see some lists here, like for example, prefetch aware shared resource management or DRAM controller co-design, cache interference management, and many more. So what the future may bring, the memory QoS techniques for heterogeneous SoC systems are essential, and many accelerators processing in near memory, like better predictability, higher performance. Combinations of memory QoS performance techniques like data mapping and scheduling, and at the same time using machine learning techniques to manage resources. And this is quite interesting that we also discussed in the beginning of this course, like using data-driven architectures that you use the machine learning techniques to learn from your data. And also we also showed some memory controller, right? Using self-optimized memory controller that was learning from the application and data characteristics. Okay, so with that, I'm gonna conclude this lecture. Any questions? Okay, I think it's too early for break. Who wants the break now? Okay, no. Can we switch the next lecture? Everything looks good on Zoom. And okay. Finally, we are into this topic, which I'm quite also excited about. Emerging memory technologies. So in this lecture, we're gonna discuss a little bit about what are these emerging memory technologies. We're gonna see some case studies and techniques that we have developed and other people have developed to enable these technologies. As we also discussed in the past, like DRAM, we showed a lot of scalability issues for DRAM. And it's true that we need to work on DRAM and make it smarter, like using intelligent memory controllers, such that you can push the boundaries and make DRAM better and better. But at the same time, it's also good to think about other memory technologies that they can potentially replace DRAM or some other also memory basically modules, not only DRAM. So if you think about flash memory was also emerging memory technologies in the very, very past. I'm actually not very, very past, like in 1980s or back then, basically. And people have worked on it to make it work. And there were also a lot of people that were quite pessimistic about this architecture. But at some point, all these researches and development that people have made, that paid off. And now flash memories are, I would say, one of the key reasons that we all can have these smartphones in our pockets. Otherwise, how can I carry a smartphone that has, for example, hard disk, and it's gonna like rotate in my pocket, it's just impossible, right? So we're gonna actually have a very thorough lecture on flash memory and solid state drives next week. So stay tuned for that. But today we are gonna also look into more, memory technologies, like they are still emerging. So flash memory is not considered emerging anymore, I would say. So it was emerging in the past. Okay. So we discussed a lot about limits of charge memory. Let's just, as a very quick reminder to jog your memory. So we have difficult charge placement and control. In flash memory, we have a floating gate, and you need to control the charge in that floating gate. We're gonna learn about background of flash memory in detail actually next week, so I don't want to spend much time today. And for DRAM also, we have this capacitor that you need to store charge. And essentially there is this transistor leakage. In flash also, you have some leakage. It's not that fast as DRAM. So in DRAM, you need frequent refresh. But in flash memory also, you need to do refresh at some point. So if you, for example, store data in your flash memory and don't touch your flash memory for a few years, it's very unlikely that you can recover your data nicely. There might be some data that you cannot even recover them at all. But fortunately, our flash memories are implemented and are integrated into SSDs now. And SSD use a quite intelligent controller, SSD controller and flash controller. And those controllers actually, do a lot of intelligent stuff to make flash work. But we're gonna learn about them next week, hopefully. Okay, so reliable sensing becomes difficult, charge storage unit size reduces. And that's quite understandable. So when you want to scale it down, it will get really, smaller and smaller. And at some point, you cannot do reliable sensing because you cannot reliably store charge and you cannot reliably sense that charge. So that's why these architectures have fundamentally basically scaling issues. We discussed about different solutions, like the solution one was the new memory architectures that we want to overcome memory shortcomings with memory-centric system design, for example, novel memory architectures, interfaces, functions, better waste management that, for example, you have seen in our latency work, that we don't need to design always for the worst case thing, and also for the voltage, or for refreshing, for example. So there are some key issues to tackle, and we actually tackled many of them in the works that we have discussed in the past few weeks, like to enable reliability at low cost, reduce energy, reduce latency. You have seen a lot in our lectures, how to improve bandwidth, how to reduce waste, and enable computation close to data. There were also some works that we didn't discuss, like compression. For example, we didn't discuss memory compression, that you can compress your data to improve your effective capacity. And that can be quite useful in order to provide the, let's say, you can utilize your current memory capacity for more data. And that can actually solve some of the basically push for more scaling and scale. Because one reason to do more scaling and scaling is to provide capacity, provide density. But sometimes by using this compression, you can, for example, with the same capacity, you can store, let's say, 4 times, larger data. And these are some works that we also have discussed some of them in the past weeks. But now we want to focus on solution 2, which is emerging memory technologies. There are some emerging resistive memory technologies, and they seem more scalable than DRAM, and they are also non-volatile. Remember that DRAM is volatile, meaning that you need to have it connected to the, the electricity to keep it charged, and you also refresh it. But these resistive memory, they are non-volatile, so they don't need electricity to keep their data. There are some examples. Here, one, like phase change memory. Data is stored by changing phase of material. There is this material here, which we'll see about it in a few next slides. But basically, depending on the phase of this material that can have 2 phases, amorphous and crystalline, you can consider like 0 and 1. You can decode it, encode it to that. And data read by detecting materials resistance. This actually PCM has been developed in 1960s, if I'm not mistaken. And this has been actually used in rewritable CDs. Because these PCM, like the material also has different light reflectivity. So if you shine light on the material, and depending on how the material reflects that, you can actually encode 0 and 1. And that has been used to write CDs and basically rewritable CDs. Of course, that's not a fast writing or programming and reading process, but that has been used for rewritable CDs. But later on, people have worked on it and realized that that phase of material can also cause resistive memory, and that can be also translated to electrical current. And people design some circuits, some sensing circuitry, if you will. And based on that circuitry, they could, decode the state of that material, and they can encode it to 0 and 1. IBM, for example, has done a lot of work in this area. Intel and other companies have done as well. So this is one of the work, one of the earliest work, I guess, from IBM, which has published in IBM Journal of Research and Development in 2008. And they designed a prototype of PCM at 20 nanometer. And this is also quite interesting that you can see that this prototype in 2008 was in 20 nanometer, while DRAM technology reached to that around 20 nanometer in 2015 or so. So that showed these architectures are easier to scale. This is clear. And when DRAM also reached to that 20 nanometer scale, then you observe more issues as well. And it's interesting that these architectures are expected to be denser than DRAM as well, because they can store multiple bits per cell. So here in my example, I said that you're resistive, you can encode it to 0 and 1, but if you chop that resistive window into, let's say, 4 regions, you can encode it to 2 bits, for example. Or if you chop it to 8 regions, you can encode it to 3 bits, for example. Of course, at some point, it might not be reliable, but this is possible. And people have done that, for example, flash memory that we're gonna see later. However, emerging technologies have many shortcomings. And the question is that, can they be enabled to replace, which is quite hard to achieve? But augmenting and surpass DRAM might be easier. I mean, by augmenting to DRAM might be easier. But basically, this is gonna be the topic of this lecture that we're gonna see. And we're gonna actually touch upon all these techniques. Like, for example, can we replace DRAM completely with PCM? Or can we, but augmenting, can we use PCM and DRAM together? Or can we use some, so there are some also characteristics of these technologies that they are not available in DRAM. For example, as we discussed, these architecture, these memory technologies are non-volatile. That means you can, for example, use them for persistent memory. Currently, when you have persistent data, you always need to rely on your disk or SSD, essentially. But if you have a main memory, which is non-volatile, you can also consider that as a persistent memory, and you can program that and use that as a persistent memory. So that can actually improve the performance for many database, for example, applications, because you have much faster access for persistent memory. Yeah, we're gonna see a lot about these topics. And here are some example works that we're gonna also discuss today. Not all of them, of course. But yeah, so industry also looked into this architecture, and this was one of the architectures that was commercialized. Intel obtained persistent memory in 2019. This is, of course, non-volatile memory based on 3D X-point technology. They call it 3D X-point technology, but if you really look into the data sheet and learn papers about it, it's essentially very much similar to PCM. So, yeah, but they call it 3D X-point. I'm not sure if it's still available to buy because Intel put this Optane out of the business, but in the past it was available. Maybe it's still available to buy, but not sure. Does anyone know? Yeah, but back then was also quite expensive to buy. But people have bought these DIMMs and they put these DIMMs to their computers, for example, as a replacement of the DRAM, for example, and they have done a lot of research on them, to how they can help. But that's good that we are also observing movement from industry for these emerging memory technologies. This paper is going to be one of the main papers that we're going to discuss today, that we want to discuss how we can architect phase change memory as a scalable DRAM alternative. So here we are quite aggressive. So we want to just replace DRAM completely with PCM, and then we want to see how it works. And then if it's not good, how can we fix it, shortcomings, or how can we eliminate them to make it happen? And Yeah, so if you want to learn more, also you can check this, but we will also discuss this paper today. So now let's also get, before going into too much detail, let's discuss a little bit back about charge versus resistive memories. So in charge memory, like DRAM and flash, you write data by capturing charge and read data by detecting voltage, essentially. In resistive memory, like PCM, STM-RAM that you're gonna see later, and memory store that you're gonna also see later, you write data by pulsing current, and you read data by detecting resistance R. So that's the main difference. There are promising resistive memory technologies like PCM that you inject current to change material phase, and resistance determined by phase. In STM-RAM, you inject current to change magnet polarity. So in STM-RAM, you have there is a magnet, quite a small magnet. You can call it nanomagnet, let's say, and resistance determined by polarity of that magnet, essentially. Memory store, RAM, and ReRAM that we're not going to discuss a lot about them today, but they also have similar, basically fundamentals, I would say, similar like approach. Like you inject current to change atomic structure, and resistance determined by atom distance, basically. But basically, you can change there is a way that you can change or determine resistance, and that's the key difference here. That provides a lot of good things because resistance, as we discussed, is non-volatile, and for resistance, you can actually fundamentally you can basically scale it down easier. But at the same time, also provides some other issues, like when you want to inject current and change these polarity, for example, in STM-RAM, change magnet polarity, or in PCM, change material phase. Essentially, you need to spend a lot of energy, a lot of temperature, and those will cause a lot of issues that we're going to see. We will start with PCM. What is phase change memory? Phase change material is Colgonite glass, exists in two states: amorphous, which is low optical reflexivity and high electrical resistivity, and crystalline, which is high optical reflexivity and low electrical resistivity. So we already discussed that using these optical reflexivities, you can actually use that for rewritable CDs. But now we are more interested in their differences in electrical resistivity. So this is the PCM material that you have. Essentially, this is the material, and this is the heater, and the metal, which is the access. Like this is the access transistor here. And you can consider your resistance here as a variable resistance that you can tune the resistance by that. So PCM is a resistive memory, and in high resistance, you can encode it to 0, for example, and low resistance, you can encode it to 1. And PCM still can be switched between states reliably and quickly, but that quickly we'll see. It's not that quick. It's not as quick as, for example, DRAM. So how does PCM work? When you want to write, you need to change a phase via current injection. So there's two basically fundamental operations: set and reset. For set, you need to sustain a current like this. You need to sustain current to heat cell above the temperature, like crystalline temperature. So you provide a current, and you need to keep it sustainable such that you can heat up that material above the temperature for crystalline. It's very important that you need to do it longer time. So that's the main difference here. For reset operation, you basically inject quite high current, so cell heated above melting temperature, and you quickly quench it. And that can cause, basically, you can get to amorphous, essentially, state. And then for reading, you need to detect phase via this material resistance, like you're in amorphous or crystalline. interesting thing is that when you do set and for crystalline, you will get to the resistance of 1K to 10K ohm, basically. But in the amorphous state, you have high resistance, and this is quite a lot, like 1 mega ohm around, or 10 mega ohm. So you can see clear difference between these two resistance states. And that huge difference is important in order to make it possible that you can read reliably from these memory. So there are some opportunity that PCM provides, like it scales better than DRAM, flash, and flash. It requires current pulses, which scale linearly with feature size, and is expected to scale to 9 nanometer. That's the report from ITRS in 2022. And we have even prototype at 20 nanometer from IBM work. And can be denser than DRAM because, first of all, it can actually scale down better, but also it can store multiple bits per cell due to the large resistance range. There are some prototypes with 2 bits per cell, like in this paper, in this conference, ISSCC, and 4 bits per cell in another prototype in 2012. But there is, of course, a trade-off between that. So when you increase the number of bits per cell, so you observe that you had quite good difference between these resistance value, right? So difference is quite large if you consider you have only 2 states. But if you want to chop it down to 4 states, then the differences is not that huge. If you want to chop it down to 16 states in order to store 4 bits, for example, then your difference is not that much. And then that's the problem. The problem is that your sensing circuitry needs to be quite accurate to detect the differences, basically. Any question? Yeah. Like how expensive? Yeah. Yeah, here also it's not. Yeah, I cannot say it's cheap. It's expensive, of course. But similar to DRAM, the overhead can be amortized when you design a main memory because you are shading that circuitry from several, for the whole array, for example. So if you want to have many small emerging memory technologies, and put all this sensing circuitry for all of them, then yes, the overhead might be actually huge, right? But as long as you have sensing circuitry and you are using that for a quite, big array, then the cost can be amortized. It's very similar to DRAM, of course, also. I don't really have that number or on top of my head. Any other questions? Okay, but that's very good questions. Yeah, and PCM is also non-volatile. It can retain data for more than 10 years at 85 centigrades, which is quite good. So without refreshing the PCM, the retention time is greater than 10 years. No refresh needed, low idle power. So here we will discuss that how we can chop this resistance value, like 1 and 0, we can chop it down to 2. We can also have multi-level cell PCM as we discussed, and you can chop it down, for example, chop this cell resistance window to 4, for example. Here you are storing 2 bits per cell. Then, of course, you have less margin between values and need more precise sensing modification of cell contents, higher latency and energy, and 2 times for reads, for example, and 4 times for writes. So compared to SLC, like single level cell PCM, here you need to spend more time and more energy in order to read and write, essentially, which makes sense, I guess. Does it make sense to you as well? Because you need to control it more, So phase change memory properties. We wanted to learn about PCM properties, and we did some survey prototypes from 2003 to 2008 from different conferences, including ITRS, electron devices meetings, for example, VLSI, and so on and so forth. And there were some people that they were working on that, and they were designing prototypes, reporting characteristics. So we look into all these numbers, and we come up with this table, essentially. So you can see that, like, for example, there are some prototypes that you don't know much, unfortunately. So there are only like this set time, which is like 100 nanoseconds, like the set current, which is 200 microampere, reset time, which is 50 nanosecond, and reset current, which is 600 microampere. And also, of course, you have this write endurance. Do you know what is endurance? We're going to actually learn about it. But it means that essentially how many times you can write to your cell reliably. So if you, for example, in this prototype, if you write to that PCM cell more than 10 to the power 7, then you can think of like that your cell is going to be dead, basically. There are different reasons for that. And sometimes your cell is not dead, but it's not reliable. Then that means in order to avoid errors, you need much powerful, let's say, ECC thing. And that's going to cause a lot of issues. But there are also some memories that after this endurance, they are completely dead. For example, they have this stuck at 0, for example. So every time you access it, you will only read 0, for example, you know. So endurance is actually one of the unfortunate issues of all these emerging memory technologies, unfortunately. And you can see that endurance for PCM, like the survey that we had from different works, is ranging from 10 to the power 4, which is quite pessimistic, in my opinion, to 10 to the power 9 or so, which seems a bit optimistic. So yeah, so you can see that basically when you want to do research on emerging memory technologies, you don't know much, unfortunately. So we look into many reports from prototypes, from industry, from academia, and we wanted to just get some numbers, but you can see that essentially these numbers are not also consistent much, because sometimes people have used different methodologies. People may have designed actually different sensing circuitry, so the sensing circuitry can be also different. So how are you gonna use these numbers? So yeah, that bring me also to this part of the doing research in emerging memory technologies or emerging technology. Essentially, it's not easy, and you always need to make some estimations, some guess, and working on a range of parameters is always a good idea. So it's very hard to pick on one parameter or say that read latency of PCM is, for example, 4 times longer than DRAM. That might not be a very good decision. So it's better that you consider a range, for example, and you show the sensitivity of your design while you're varying this parameter, for example. Okay, let me discuss about this few next slide, and then we can take a break. So where can PCM fit in the system? We have this main memory, caches, and storage. We wanted to replace it as consider as a main memory. If you look into this plot here, like this scale, you can see that the x-axis is the typical access latency in terms of processor cycles for a 4 gigahertz processor. So for example, here L1 cache is here, like the access is around 2 cycles, and we have last level cache and main memory system, like DRAM, and also disk. So you can see that between DRAM and hard disk drive, we have quite a lot like gap, and that's why actually Flash found its way nicely, So Flash filled the gap nicely between hard disk drive and DRAM. So now the question is that how PCM can find its way, for example. So PCM latencies are close to DRAM, but not as good as DRAM. So, but yeah, in this work, we'd like to see how we can use PCM for DRAM. Read latency of PCM is around 50 nanosecond. I mean, using all these study, for example, which is 4 times longer than DRAM, but it's faster than NAND flash memory, for example. Write latency is around 150 nanosecond, which is 12 times longer than DRAM. Write bandwidth is also lower than DRAM and is similar to NAND flash memory. Dynamic energy is, unfortunately, is also higher than DRAM, like 2 times. I assume 2 times is for read. So read dynamic energy for PCM is 2 times of DRAM, and write dynamic energy you consume for write is 43 times larger than DRAM. And dynamic energy is similar to NAND flash. And for endurance, it's like 10 to the power minus 8 times of DRAM. So for DRAM, we don't know actually endurance because there is no report for that. We don't know actually if DRAM has endurance problem or not. At least we haven't observed endurance problem of DRAM until we use our system. At some point, you just wear out your whole system as well. But DRAM also doesn't, I mean, at least from what we can also see, the architecture doesn't have that kind of issues that can cause endurance problem. But in PCM, clearly we have that problem. But as a good thing, cell size is better than DRAM. So basically, it's denser, and you can also scale it better with using MLC technique. Sorry, actually, cell size is larger. Cell size is larger than DRAM, but it's not that larger. It's also larger than NAND flash memory. But you can also scale it better with feature size and using MLC technology. So yeah, the takeaway here is that you can see that it's very unlikely that PCM can replace DRAM because there are many shortcomings. But yeah, let's conclude again about pros and cons over DRAM. Like the pros is that we have better technology scaling, as we discussed. We have non-volatility, persistent memory, and low idle power. So we don't have a refreshing issue. But we have higher latencies, higher active energy, and lower endurance and reliability issues. So we don't, for example, have issues like RowHammer, for example, you know, that you have this read disturbance, for example, it's not, but you have similar other issues here as well in PCM, that accessing your PCM or memory at some point can cause some resistance shift. So your resistance window can shift. And if you don't update your references, you're gonna read basically wrongly. And that's also the case for flash memory. And that's why we always need to update our reference voltage for flash memory as well. So there are challenges in enabling PCM and DRAM replacement. So to mitigate PCM shortcomings and find the right way to place PCM in the system. So here are different examples, like this system can be like completely DRAM. This one is most likely the way that we're gonna have PCM in the future, probably, if we have. It's gonna be kind of hybrid that you have both DRAM and PCM. And also a bit like more aggressive solution that you completely replace DRAM with PCM. So this work that we will discuss today is actually considered this hybrid solution, and this work that we're gonna also discuss consider completely replacement of DRAM. And that was one of the initial study that we want to replace DRAM completely with PCM. Okay, so before going into this paper, let's have any question before. Yes. Yes. So you have some circuitry, right? Sensing circuitry, and those are, you know, CMOS based probably or whatever. So they also consume some power. Yeah. Any other questions? I mean, that's one reason I can think of, but can be also other things. Okay, so let's take a break until 2:35. for 10 minutes, and then we will continue from this part. Thank you. Okay. Okay, let's continue. Am I audible on Zoom? So we want to completely replace DRAM with PCM in this work. And here are the numbers that we consider. Like for the latency is like 4 times higher read latency, 12 times longer write latency. Energy is 2 times for read and 43 times for writes. And endurance is also 10 to the power 8. So these are the numbers that we come up from all these surveys. And we did some simulation that with basically we replaced DRAM with PCM with in a 4-core, 4 megabyte L2 system. And PCM organized the same as DRAM. So we consider that basically PCM is designed as architecture is completely like a DRAM array, like the row buffer, banks, peripherals, everything the same. But we just consider that, okay, when you access that cell, you need to spend more time, for time. So at the simulation level, you can do such things, right? So the long story short is that results are not good. So we have around 60% longer execution time, 2.2 times energy, higher energy, and 500-hour average lifetime. And this is actually average. There are some applications that basically the lifetime is even much lower, like for FFT, for example. And there are some applications that delay, like this is also 60% is on average. For some applications, our performance overhead is much more. So the results are not good. And that's kind of we were expecting, by just replacing all these numbers. You cannot get good performance, of course, and good energy. But now the question is that, can we overcome these issues? And we look into it. So this paper have discussed different ideas that we don't have time to look into it, but I'm gonna only showcase 2 ideas of that paper. The first idea is that we can use multiple narrow row buffers in each PCM chip. So in DRAM, we have a big sense amplifier because while you're reading from DRAM, read operation is destructive, right? And you need to this sense amplifier to do this charge iteration to make sure that everything is correct. But PCM doesn't have that issue, right? So you don't need that sense amplifier to be as big as the whole array, the whole like the row of the DRAM. So you can actually have a smaller size sense amplifier, and with that you gain some area, like area budget, and you can use that area budget to add some latches, some buffers. And with those latches and buffers, you can essentially hide latencies. So they can act as your cache, if you will. Make sense? Yeah. Yeah, in PCM, we don't need basically sense amplifier as big as the whole row. So you can just put the sense amplifier for a few blocks or whatever that you're reading. You care at that moment. Yeah, it can come into, yes, less row buffer locality. Yeah, but you can do that consecutive of time, right? So there are different ways. So you need to basically, fill up these latches. You can fill up these latches, and these latches can be filled up by this blocks or words from the same row, by reading, consecutively into the time, or you can actually fill up these latches from different rows. So that's a key difference here, But in DRAM, you cannot do that at all because, yeah, so essentially that sense amplifier should, although there are some new DRAM architectures like sector DRAM that Atoberg, has published recently, that, by redesigning DRAM architecture, you can actually also implement some lower granularity access. But in general, it's not easy in DRAM. Yeah, that's a good question. The second idea is that we want to write into array at cache block or word granularity. So you don't need to. So in DRAM, when you want to write, you write to the sense amplifier essentially, and then you need to basically wait such that that value which is in that write buffer should be restored in the DRAM row. But here in PCM, you don't have to basically, update the whole row. You can only update the part that is different. Maybe you only change a byte, or 2 bytes, or a word, or a cache block. So you only want to update that, and that can essentially reduce a lot of basically write cycles. Remember that we have this endurance issue. So with that, you can reduce the number of writes. There are actually some works that they also look into it a bit even more aggressively, and they want to control individual bits. Samsung has done also work in that. And so essentially, whenever you want to write, you only update bits. You only write to bits that they are different. So you capture, you read what you have, and you know what you want to write. And there are some differences, and you only program those differences. And that can essentially reduce a lot of programs. So these two ideas, by implementing them, you can get like performance improvement compared to the baseline that you had, but still you're increasing the execution time by 20%. Your energy consumption is on par, and the average lifetime is longer. Still, there are some applications that, the lifetime is not that long, but for the average is good. But there are some caveats here. First of all, worst case lifetime is much shorter. So we don't have guarantee here, which is not good. Second caveat is that intensive applications see large performance and energy hits, which is again expected. And caveat 3 is that, do we even consider optimistic PCM parameters? Because we didn't know, right? We surveyed through a lot of papers and we come up with these set of parameters, but are these parameters even optimistic or pessimistic? It turns out actually in future that some of these parameters was actually very optimistic. Some of them not that, maybe even pessimistic, but some of them optimistic. So that's the thing. So when you're, if you're thinking of completely replacing main memory with PCM, then you don't get performance improvement, while you get degradation. And also there are some issues like there is no guarantee on lifetime and many other things that we already discussed. If you want to learn more, you can check this paper. And this is also the DIM that we discussed about it, like Intel Optane, that realized in 2019, which again, technology 3D explained, but it's very similar to PCM. Yeah, and so of course, when you have this PCM-based main memory, you can also think about how you can do efficient data mapping and buffering techniques for multi-level cell phase change memories. I think I'm gonna, I have some slides for that a bit. So yeah, essentially, the thing is that when you, maybe this, so when you have multi-level cells, like here, you're storing 2 bits in one cell. So you have different latencies when you want to write, essentially. You can see that, right? So you need to, if you want to write 1-1, you can actually do it quite fast. But when you want to write 1-0, you need to wait more, and 0-1 longer, and 0-0 longer. So that's the difference. So then we have this observation that we have asymmetry in reads. The read latency and energy of bit 1 is lower than of bit 0. Why is that? You can actually see here. Like the bit 1 is the most significant bit. In order to ensure the most significant bit, you only need to wait until T2. right? But if you want to make sure about the least significant bit, you need to wait until T4. So you have this asymmetric. So yeah, if you can also show, we can also show it in this simplified example that there is a capacitor field with reference voltage, and when we connect MLC PCM cell with unknown resistance, depending on what's the resistance, this is actually the simplified version of our sensing circuitry. Depending on the depending on the resistance of that, you might have different current basically, and that current would determine how fast this capacitor will be basically decharged. So yeah, in here you can see that this was the initial voltage of that capacitor, and we connect it, and then if this amount of time takes to discharge that capacitor, we can then encode it to 0, 1 basically, right? So in existing devices, both MLC bits are read at the same time, and we must wait maximum time to read both bits. However, we can infer information about bit 1 before this time, and then we can only basically, we can use that, like, so time to determine bits 1's value, like the most significant bit, is faster. So we can actually read faster for that. So how you can benefit from that? There are different ways, which I'm not going into detail of that, but you can think of, for example, you can consider one page of memory in MSB and the other page in LSB, basically. And the page that you have in most significant bit is faster, and LSB is slower. And then you can think of how you can handle it or control it as like a cache, for example. You know, that data that they are latency sensitive, you can map them to the pages that they are mapped to the MSB bits, that they are faster, and the other to the LSB. So there are different ways. This one just an example. But for that, you can also read the paper for more detail. We also have asymmetry for writes. Depending on what's the initial state we have different latencies to get the final value. So essentially, for example, when the value is 0, 1, and we want to go to the state of 0, 0, you have quite, it's quite faster, for example. So you can also use that and benefit potentially from that by using data mapping and buffering techniques. I haven't discussed, I haven't explained like how these can be implemented, like how you can benefit from these techniques. If you want, you can also check this paper, but you can assume from the example I mentioned, I guess. Any questions? Now we want to see how STT-MRAM can replace as main memory. First of all, let's see what is STT-MRAM. STT-MRAM has magnetic tunnel junction, MTJ device. You can see the device here. And there is a reference layer with a fixed magnetic orientation. This is the reference layer. And there is also free layer that it can be parallel or anti-parallel. So when you have this free layer parallel with the reference layer, you can encode it to logical 0. And when it is anti-parallel, you can encode it as logical 1, for example. So magnetic orientation of the free layer determines logical state of device, high versus low resistance. And for write, you need to push large current through MTJ to change orientation of free layer, essentially. And for read, you need to sense current flow, essentially. If you want to learn more about STT-MRAM, this paper you can actually check. People have looked into using STT-MRAM instead of actually SRAM as well, because latencies of STT-MRAM is actually, you're gonna see that it's actually much better than DRAM, but they are not better than SRAM. But at the same time, the problem with STT-MRAM is density. So unfortunately, STT-MRAM is not as dense as DRAM. So their density is very similar to SRAM. So that's why people also look into how they can use STT-MRAM and SRAM together, and they design different architectures like caches for GPU, CPU, and other basically devices. But in this work, we are discussing about how we can use STT-MRAM as a replacement for DRAM. So there are some pros over DRAM, like better technology scaling, capacity, and cost. And it's non-volatile again, so it's good, persistent, and low idle power. At the same time, also STT-MRAM latencies might be even faster than DRAM as well. But there are also cons. For write latency, unfortunately, STT-MRAM has higher write latency. And so for read latency, STT-MRAM might be better. And write energy is also high. Unfortunately, it has poor density. And reliability of STT-MRAM is also questionable. So for STT-MRAM, there are still a lot of work going on to see, to make it reliable. So that's why we have this question mark here. But this memory technology is actually quite interesting because of this level of freedom as well. So you can trade off non-volatility of this memory for lower write latency and energy. So when you reduce the size of this MTJ, you can reduce retention time. Potentially, at some point, your retention time is not that high, such that you need to refresh it. But for memories like cache that you frequently update data, or register file, for example, that you frequently update that, you may not need that actually high retention time as well, right? So you can think of this trade-off by reducing this MTJ, and that essentially cause a lot of reduction in write latency and energy, but at the price of non-volatility. I mean, like reducing non-volatility characteristics. So at some point, your STT-MRAM actually needs refreshing, and people look into it. People are even looking to designing different STT-MRAM architectures in one chip, like as a cache. They have some STT-MRAM part that they consider as a high retention, which is slow. They consider as a like bigger cache, and also a smaller STT-MRAM cache, which has low retention time but is faster. And they try to, cache most of the important, like the working set in that basically smaller resistance, like the STT-MRAM cache. So it's quite interesting that you have this level of freedom and you can do a lot of trade-off analysis here as well. So by architecting STT-MRAM as main memory, you can see in the same methodology, you can see that we have less performance loss compared to PCM. So it's only 6%. And we even have 60% energy saving compared to DRAM, which is good. So that's why actually STT-MRAM has some potential to basically replace DRAM. But at the same time, the problem, as I said, is its density and its reliability. So it's not still clear. And you can check this paper for more detail as well if you are. But now let's look into the other approach, which is hybrid main memory. Remember this picture from the past that we discussed about like having like CPU and different controller. So you have DRAM controller, for example, that control DRAM, which is fast and durable. However, it's small, leaky, volatile, and high cost. And there can be another memory technology like phase change memory, which is large, non-volatile, and low cost. However, it's slow, wears out, and has high active energy. So while using these two together, hopefully you're gonna benefit from, to achieve the best of multiple technologies. So that's the idea of using this as a hybrid memory. But of course, this also has a lot of challenges. For example, how do you map your data? How you decide which data should go to DRAM, which should go to PCM, for example? How you migrate them, and or are you going to architect it as a cache, like the DRAM is going to be the cache for PCM, or DRAM is part of the memory address space? So like DRAM and phase change memory together, constructs the whole memory address space. So that's if that's the case, then the programmer needs to work on it as well. Like use some, have some instructions to store data in DRAM part, or some instructions to store data in PCM part, for example, or compiler can also help. But it can be also as a cache, like DRAM can be cached for the PCM. I should also say that this doesn't need to be at the only main memory. There has been work that people try to use this hybrid STT-MRAM, SRAM cache, for example. In my PhD, actually, I did also research on designing hybrid register file that I used the SRAM with a non-volatile memory as a GPU register file. So it can be also in that level, at the register file of GPU, for example. It can be actually also at the storage system, that you have different storage devices with different characteristics, and you want to design it this hybrid technique. But this is quite interesting. So the goal is to providing the best of multiple metrics with multiple memory technologies. And that's the area that basically heterogeneity comes to play, and configurable, programmable memory systems. Of course, as I said, there are many questions or challenges to address, like are we designing as a cache versus main memory, as I discussed? What should be the granularity of the data movement or management? It should be fine grain or coarse grain. It should be hardware control or software or hardware software cooperative. As you can guess, probably should be hardware software cooperative. When to migrate data, because migration is always costly. So when to schedule it, essentially. And how to design a scalable and efficient large cache. Sometimes if you want to use it as a cache, that cache is going to be quite large. It can be like tens of or hundreds of gigabytes, right? So that cache is quite large. So how do you design it? Like the tag array is going to be also huge. So these are very important questions and hard questions that they are hard to answer. But one option is that we can consider DRAM as a cache for PCM. So PCM is a main memory, and DRAM caches memory rows and blocks. The benefit is that it reduces latency on DRAM cache hit, and it also does write filtering. So it can improve it can eliminate the write endurance problem of PCM. And memory controller hardware should manage the DRAM cache. So benefits is that it eliminates system software overhead. But there are at least 3 issues. So what data should be placed in DRAM versus kept in PCM? So how you're going to manage your cache intelligently, essentially. And what's the granularity of data movement across them, and how to design a low-cost hardware manage the DRAM cache. So there are 2 idea directions here, like locality-aware data placement and chip tag stores and dynamic granularity that we're going to also see a little bit later. So DRAM as a cache for PCM, the goal, as we discussed, is that achieve the best of both DRAM and PCM, or NVM. So it minimizes the amount of DRAM without sacrificing performance and endurance, and DRAM as cache to tolerate PCM latency and write bandwidth. And of course, PCM as main memory to provide large capacity at good cost and power. So here is your DRAM buffer. How you manage your DRAM buffer is a very good question to ask. And there are some techniques that this paper also discussed. Like for light filtering techniques, you can actually have this approach of lazy writes. When you bring data from flash or hard disk drive, you don't write them immediately to PCM. You first write them to this DRAM buffer as a lazy write, and pages. And then after all, if you realize that they are needed, or basically, or they are dirty because you capture some writes in that DRAM buffer. So you need to write them back to this PCM. But at some point, you don't need to write them back even to PCM. You just write them back to the flash or hard disk drive. So you can also do this page bypass. So you just discard pages with poor reuse on DRAM evacuation. If you want to learn more about detail, you can check this paper, of course. Here are some results. So this paper did some analysis. The simulation that they have done is actually a bit at a higher level compared to what we have done in the other work that I showed. It's actually like it's a combination of also some analytical models they have. But essentially, they consider that they have the simulation of 16 core system with 8 GB DRAM. And the main memory access is at 320 cycles. It has also HDD at 2 milliseconds with also flash memory at 32 microseconds. And they consider that flash hit rate is 99%. So 99% of requests will hit in flash, and you don't need to go to the HDD. And their assumption was that PCM is 4 times denser. So here they even also consider this good thing about PCM. So in our work, in the other work that I discussed, we haven't, we consider that both PCM and DRAM, they have the same density. We only take into account difference between their latencies and like access latencies and energy consumption. But here in this work, they consider that PCM is also denser. So they are using these properties to provide better performance. And they also consider that PCM is 4 times slower than DRAM, which is quite optimistic in my opinion. Like in our work, for example, we consider that PCM was 12 times, like at least the write latency, 12 times longer than DRAM. And DRAM block size is equals to PCM page size. So you can see some results here that like while you go from, and the y-axis is normalized execution time, so lower the better. And here are some workloads from IBM, assume. And so when you have this 8 GB DRAM, results are normalized to this baseline. So having a PCM memory as a standalone memory with 32 GB, you actually, on average, you observe some performance benefit. Why is that? Because you have larger memory. So now you are actually interfering the good thing about having a larger capacity DRAM. So once you have larger memory, you access flash less frequently, right? So that's why you're observing better performance compared to DRAM. But comparing these two baseline, like the PCM and DRAM, they both have exactly the same capacity. You can see that DRAM provides better performance. And actually, these results is very similar to the results that we also we reported in that work. Actually, this paper and that work was quite parallel. Both of them was published in ISCA 2009. So it's also quite interesting in that sense as well. But having a 32 GB PCM plus 1 GB DRAM as a cache, you can actually get the performance benefit. And the performance on average is quite close to 32 GB DRAM baseline. So you can almost get the performance of 32 GB DRAM by using 32 GB PCM plus 1 GB DRAM as a cache, which is good. We wanted that actually from a hybrid memory system. Clear? Okay, great. So yeah, here also we discuss about power, energy, and also the lifetime. You can see that basically the hybrid design provides better like energy consumption and better energy delay, like the kind of energy efficiency metric. And the average lifetime is around also 10 years. But of course, there is no guarantees because worst case scenario can actually wear out your system quite fast. Yeah, but if you want to learn more, you can check this paper. Actually, yes, it was also from IBM research. Scalable high-performance main memory system using phase change memory technology. Any question? Yes. Yes. Yeah. Yes. Very good question. And that's true. We will have one brief slide actually on that at the end. But yeah, potentially that's actually one of the issues as well. In DRAM, you need to do that cold boot attack, but you really need to, cold your DRAM a lot, to very low temperatures such that retention time is long enough, such that, you can just remove your DRAM from that system and put it on another system. But with non-volatile memory, everything is there, like non-volatile. Right? So they potentially you can actually steal data and have security issues. And people have done research on that as well. Very good question. Not question, actually, I would say very good comment. Okay, great. So let's think about this data placement in hybrid memory at the little bit higher abstraction. So essentially, you have these cores, caches, and memory controllers, and several channels can be. And one channel can be memory A, which is fast and small, and channel B can be memory B, which is large and slow. And the idea is that you want to basically allocate your pages to these different memories. So at some point you move page 2, you migrate page 2 to channel A because you want to have faster access. But the problem is that, so it caused some data movement. But in addition to that, now you also have some contention on channel A. So it can also comes at the price of some lower bandwidths if you implement like this as well. So which memory do we place each page in to maximize system performance? These are the questions. But at the same time, you should also answer other questions that, like, you shouldn't basically make channel B idle and potentially cause load balance issues. Okay. So data placement between DRAM and PCM, the idea is that how to characterize data access patterns and guide data placement in hybrid memory. Like there are workloads that they have streaming access. So when you have a stream access, they can be as fast in PCM as in DRAM. However, in random accesses, they are much faster in DRAM. Because for random access, you need to pay for access latency. But when you have stream access, hopefully you can hide those latencies by benefiting from your bandwidths, essentially. So that's why for the applications that they have a stream access, you can actually map them, for example, in this example to PCM, and for random accesses, you can just map them to the DRAM. And that's the idea of this work, like place random access data with some reuse. Reusability is also important. So you also need to consider some locality as well. So random accesses with some reuse, we map them to DRAM, and for streaming data to PCM. And here are more detail about it. Like, so row buffers exist in both DRAM and PCM. So row hit latency is similar in DRAM and PCM. However, row miss latency is small in DRAM and large in PCM. So that's why actually row conflict is costly for PCM. So that's why you don't like random accesses. So while you have streaming accesses, you can actually benefit from your row buffer locality. So that's why you can actually map them to DRAM or PCM, and both can work. But when you have random accesses, most likely you're gonna have a lot of row conflict, and that's why it's better to have use a memory that has less miss latency. Question? Okay. So place data in DRAM which is likely to miss in the row buffer, low row buffer locality, which miss penalty is small in DRAM and is reused many times, which is cache only the data, worse the movement costs and DRAM space. So these are the two criteria that if they are met, you can actually move that or migrate that data to the DRAM. And here are some results for that that you can see good speed up. You can check this paper also to learn more about this work, how you can benefit from row buffer locality, like make your hybrid memory management technique aware of row buffer locality, and as well as, yeah, exactly, and also memory access pattern. Okay, so yeah, there are some weaknesses of existing solutions. They are all heuristic that consider only a limited part of the memory access behavior and do not directly capture the overall system performance impact of data placement decisions. So since we don't have enough time, I'm gonna skip these slides. I'm gonna just give you some idea about it. Like in the end, you want to get some you want to define some utility technique basically utility-based hybrid memory management. So a memory management that works for any hybrid memory. So this work wanted to, to design a memory management, hybrid memory management technique that can be extended or can be applied to different baselines. So essentially, you need to define a metric which is called utility. So for each page, we need to use comprehensive characteristics to calculate estimated utility, which is a performance impact of that decision. Here, decision is migrating page from one memory to the other one. And we only migrate pages with the highest utility. And that means pages that improve system performance the most when migrated. So how we define this utility metric and how we capture it and calculate it, of course, you need also some modeling. You need some performance model at the runtime. Here you can see some formula, for example, formula for that. And based on that, you make your decisions. Yeah, but you can learn more about it as a part of your potential learning, reading as well, that you can do from homework 3, I guess. Okay, so any questions so far? Yes. Sorry? Yes. Why is that? Yeah, you can. I think you can consider the same size in that example. Yeah, in that sense. Yeah. Exactly. No, so the thing is that when you have miss in row buffer locality, you need to pay for. When you have miss in row buffer, you need to read again. You need to sense a PCM row, right? And you need to pay for PCM access latency. But when you have row hit, you just need to pay for kind of a SRAM access latency, right? Because row buffer is essentially the SRAM memory kind of things, right? Okay. So yeah, there are a challenge and opportunity like enabling an emerging technology to augment DRAM and managing hybrid memories, and designing effective large DRAM cache is one issue here. So let's also look into this problem that we have with large DRAM caches. So when you have this large DRAM cache, it requires a large metadata like tag plus block-based information store. How do we design an efficient DRAM cache, basically? So when you issue a load request, you first check you want to see if the data can be achieved from this DRAM cache, right? So you need to check the metadata. So you need to access it, and then if it's hit, you can get the data from DRAM, basically. Otherwise, you should go to the PCM. So the idea is that how we store tags. So if you store tags in the same, one idea is that we can store tags in the same row as data in the DRAM. So in your DRAM row, you have cache blocks, and also you have tags. So unfortunately, the downside is that, I mean, the benefit is that you don't need the on-chip tag storage overhead, because actually that's huge overhead. Your tag array needs to be quite high. You can actually do some calculation at home, but essentially that's because your cache, your DRAM cache is quite big here, and then you need quite large tag array metadata. So you don't need to pay for that, but there are some downsides, like cache hit determined only after a DRAM access, which is quite basically time consuming. And cache hit requires 2 DRAM accesses. So you need to access DRAM to get the tag. And then after checking the tag, and if it's a hit, then you need to access again and read the block, basically. So that's an issue again. The second idea is that, recall the first idea, we can still store all metadata in DRAM, but we can reduce metadata storage overhead. Sorry, we can, so that's because we want to reduce metadata storage overhead, but you can also cache a part of that metadata in an on-chip SRAM. for frequently accessed metadata. So those blocks that you are accessing them more frequently, you can cache the metadata of them in a SRAM base. So yeah, so that can actually reduce the cost for accessing metadata. So now you have probably both fast metadata access as well as also low storage overhead metadata access together. And the third idea can be like dynamic data transfer granularity. So there are some applications that benefit from caching more data. So they have good spatial locality. Potentially, you can consider that they have larger cache blocks. Others do not. So large granularity wastes bandwidth and reduce cache utilization. So the third idea is that we can have simple dynamic caching granularity policy by cost-benefit analysis to determine best DRAM cache block size. And then we can group main memory into a set of rows, for example, and then different sample rows sets follow different fixed caching granularities. And the rest of main memory follows the best granularity, for example. Yeah, you can check the paper for more detail, but with this technique, combining all these together, you can actually get the performance very, very close to the ideal case that you store, like ideal, but very costly, that you store the whole tag in the SRAM, basically. So in this baseline SRAM, the whole tag array is stored in a SRAM. But from this technique, we have tag array in the DRAM, but with all this technique that we build on top of that, we can actually get the performance very similar to that, but with quite lower complexity. In terms of energy efficiency, you can get better energy efficiency because you don't reduce performance much, but you reduce the cost and power a lot because of lower storage. Okay, so you can also check this paper if you are interested to learn more. It's going to also be part of your reading as well. But essentially, DRAM caches, there are many also recent options. People also have worked on it a lot. We have worked, other people have worked also a lot, and there are many different studies, like different that you can see here, different scheme. This paper actually has done a very nice comparison across them, like compare all these schemes or techniques in terms of like DRAM cache hit, how they handle DRAM cache hit, how they handle DRAM cache miss, how they handle replacement traffic, replacement decision, and so on and so forth. So if you're interested, you can actually check this paper as well. Okay, any questions? So now I want to look into other opportunities with emerging memory technologies. So here I'm going to list some of these basic opportunities. We're going to cover a few of them. One opportunity, potential opportunity, is merging of memory and storage. So currently they are not to merge, like we have DRAM and we have SSD or hard disk. So potentially with emerging memory technologies, because they are non-volatile, you can actually merge them and you use a single interface to manage all data. You can also consider new applications like ultra-fast checkpoint and restore, which is quite important for persistent memory. You can have more robust system design by reducing data loss. And also you can think of processing tightly coupled with memory, like using this processing in memory techniques. So recall our processing using memory lectures. I'm not gonna go over them again. Like we can do a lot of computation, for example, using DRAM, like Ambit and row clone, same DRAM. People have shown that, for example, emerging memory technologies, they can also do bulk bitwise, like bitwise operations and row clone in this work, Pinatubu. You can check it if you're interested. But interestingly, these architectures can do also some operations that processing using DRAM cannot do, for example, easily. And that's because the way that they are built, like in-memory cross-port array operations. So these architectures are like designed in a crossbar way. Like some emerging NVM technologies have crossbar array structure, like memory store, resistive RAM, phase change memory, STM-RAM. And these crossbar arrays can be used to perform dot product operations using analog computation capability. So by doing dot product operations, potentially you can do matrix vector multiplication. Potentially you can do neural network, convolutional neural network, so and many other these techniques. So they can operate on multiple pieces of data using Kirchhoff's law. And bitline current is so that's Kirchhoff's law, right? Bitline current is the sum of products of word line voltages times conductive of each cell. And computation is in analog domain, so inside the crossbar array. So that's why you need pre-flash circuitry, like digital to analog and analog to digital conversion for the inputs and outputs. Here is then one example. So you can see we have these digital to analog converters. And here is your crossbar array. This is a sample and hold, if I'm not mistaken. Like you can think of as a latch, that you sample your analog data current here, and you have analog to digital converter here. So essentially what's happening here is that the voltage that you apply here, which can be determined based on your input vector. So you have some input values like 0 and 1, and you use this DAC, like digital to analog converter, to map them to some voltage value, right? So these voltages can cause some current to this line, depending on the conductance of this resistor. And then the current value in this basically bit line is going to be sum of these current values based on Kirchhoff's law, right? So that's why you can see that this is actually kind of dot product, So you can use this analog perspective and then use it, that convert it to digital to do easily dot product. And people have done it. So I already explained this. You can also see it more from this like animations. So like this is the current value that you can get. So essentially you can consider that, for example, you have this input array, and this is your matrix, your weight matrix, and you can have your weight matrices as the resistive value in your crossbar array, and then you input all these values to the input voltages, and then you get the output essentially. So that can implement, yeah. Yeah, yeah, you need to pay for basically write energy, write latency to program like a STM-RAM, for example, right? Or ReRAM. And that's also part of the like the endurance issue. Like people have shown that, for example, using ReRAM array is quite good for inference, that you program your weights for one time, for example, and then you do a lot of inference a lot. But once you want to do training, that you need to update your weights, then your crossbar is going to wear out very, very quickly. Yeah, so, and this has been actually basically presented first in, like, people have used it for accelerating convolutional neural network in Isaac paper, for example. I do remember that paper very clearly because the first author of Isaac paper was my first mentor in 2011, when I was doing when we were doing together research on adaptive routing algorithms for interconnection network, that we're gonna also see some lectures on that as well later. But yeah, so later on he joined the University of Utah and he worked on this topic as a PhD student. Now I'm not sure where he is, but I also learned a lot from him as well. Okay, so yeah, so you can think of how you can use this idea for convolution. So here as an example of convolution, that you essentially have input feature map, and there is this window that you are moving or sliding through your input, and you are doing some computation whenever, you know, at each step, and then you calculate the output feature map essentially. So of course, you also need to do some padding such that you make sure that, you know, you always have some data, because there are some regions that your window can go outside your input feature map. So yeah, so you can actually think about it, and then you can use it for doing this operation for convolutional neural network. But in the in convolutional neural network, you don't only do basically dot product. There are also some other layers, like non-linear layers, like ReLO, that those are also, so in your chip, essentially, you can have this NVM-based PIM array that you do these dot products. And also you need to do some non-linear function array. You can consider it as a processing near memory engine that they also integrated here such that they can accelerate non-linear operations. And with that, they could basically improve performance. We also have done work on this topic, like GenPip, that John might also discuss a little bit about this work tomorrow in our genomic lecture. So in, and this work also, Swordfish, I'm not sure if we are gonna discuss it tomorrow, but it's gonna be also part of one of your reading. So this is also quite interesting because people have used ReRAM a lot, you know, these basically memory stores for doing neural networks, basically for doing this convolutional neural network or these applications, like deep neural network. But the problem is that these memory stores are non-ideal. And then as a result of that, whenever you do computation, you have some errors. So this work actually tried to look into how these errors can make your, you know, assumptions wrong, and how these, you know, essentially you get accuracy loss or performance loss by using these memories. So it's very good to know about all these issues, you know, such that you can design techniques to overcome them. Yeah, this is the Isaac paper that I mentioned, and also other papers in this area that people have developed. And it's also part of, I would say, lecture in also systolic array and convolution. If you're interested, that's a beautiful topic that you can also check from Professor Mutlu's lecture. Okay, now let's look into the other. Any questions? I like to finish the lecture, and it's doable actually, but it might be at the price of no break. But is it fine, or do you guys prefer have a like very short break, like 2 or 3 minutes? Who wants 5-minute break? Okay, then I will continue. Apparently, the topic is quite fascinating. Okay. So we discussed about merging of memory and storage. Let's jump into it a little bit more. So you can have actually, so this is a conventional system essentially, right? You have memory and you have storage. And so processor access DRAM with instructions, we load and store instructions. However, to access disk, we need to go into IO block, basically subsystem, IO block, basically stack. And you need to open file, read the IO, and then update and whatever. So that shows that whenever you want to access storage, you need to pay for a operating system overhead, essentially. And that wasn't the case in very, very early in this computer system, that we had a core memory. If you know about it, there was core memory that people used that as a main memory, as a storage, as everything. That wasn't also very big memory, but that was the only memory that people had. But later on, by advancement in technology, and people have developed like DRAM, then time to time, basically these interface actually got diverged. So now we have different interfaces to access main memory and also access storage. So we know that hard disk drive is non-volatile, but it's slow and block addressable. And we know that DRAM is volatile, fast, and byte addressable. At the same time, we also know that there are some non-volatile memory like PCM or STM RAM that they are relatively fast, at least compared to flash memory or hard disk drive. And they are byte addressable and they are non-volatile. So now the question is that, can we use these non-volatile memories to combine memory and storage such that we have one shared interface across them? So that's the idea of a two-level memory and storage model. So the traditional two-level storage model is a bottleneck with NVM. The reason is that the reason is that when you consider this example, like the two-level store, you have this processor and caches, and you need to, whenever you want to access your storage, you need to go into operating system and file system process, essentially. But that overhead might be okay because hard disk drive is slow by itself, you know. So you can pay for that overhead because that's basically IO block latency might not be that long compared to the latency of accessing hard disk drive. But it turns out that actually that's not true for SSD, and that's why people have developed emerging also interfaces to access SSDs like NVMe interface that we're going to also learn about it next week. However, if we consider that we have PCM here, so PCM is much faster than SSD, for example, than flash and than HDD. So now you need to pay a lot of latency going through the operating system, and then your access latency to that PCM is quite fast. So clearly that's not a good decision. So now you can see that this design of two-level is a bottleneck while we are using NVM, non-volatile memory, as a storage. So yeah, I already explained all this. Okay. So the goal is that we want to unify memory and storage management in a single unit to eliminate wasted work to locate, transfer, and translate data. So, and that can improve both energy and performance, of course, and simplifies programming model as well. So programming model does not need to deal with different, basically, different class of memory, and if also it's persistent or not on different interfaces. So everything is just unified. So that naturally provides program ease. So with NVM, you can provide persistent memory, as we discussed, and so that's the opportunity to manipulate persistent data directly in the NVM memory. So here is an example. For example, so you have different memory modules like DRAM, flash, NVM, and HDD, like different memory technology, let's say, and they are all at the hardware, but you are unifying the interface as a persistent memory manager, essentially. And you access this persistent memory manager between load and store, and this manager will access DRAM, flash, NVM, and HDD. So processor will only see this load and store, essentially, in the end. And there are also some hints from software, OS, and runtime, and you can use these hints to map your data intelligently across DRAM, flash, NVM, and HDD, essentially. So here's a very easy, let's say, example of persistent object. So there's a file that you just allocate it as a persistent object, and then you can map that file persistent object to flash or NVM or HDD, depending on the basically characteristics of that. Yeah, as I said, persistent memory manager uses access and hint information to allocate, locate, and migrate and access data in the heterogeneous array of devices. So the persistent memory manager exposes a load store interface to access persistent data, which that is the key difference here. And applications can directly access persistent memory. There is no conversion and translation and location overhead for persistent data. And it manages data placement, location, persistence, and security to get the best of multiple forms of storage. And also it manages metadata storage and retrieval. This can lead to overheads that need to be managed, of course, and exposes interfaces for system software, hooks and interfaces for system software. Okay, so for efficient data mapping among heterogeneous devices, just to give you some idea about it, like a persistent memory exposes a large persistent address space, but it may use many different devices to satisfy this goal. Like from fast, low capacity, volatile DRAM to slow, high capacity, non-volatile HDD or flash. So you have different, basically, memory technologies or storage devices that you can manage them nicely. And there are also other NVM devices in between. So performance and energy can benefit from good placement of data among these devices. That's why you really need to learn from these hints and map your data nicely, and utilizing the strengths of each device and avoiding their weaknesses if possible. For example, consider two important application characteristics like locality and persistence. Here is one example, like you have one applications like database applications, like columns in a column store that are scanned through only infrequently placed on flash. So clearly it has less locality because like it's infrequently and also you scan through, but it is persistent because it's part of your database. So in this like two-dimensional let's say characteristics, you can classify it as this node. At the same time, there can be some application like frequently updated index for a content delivery network like CDN. And that is has more locality and also temporary. So you need to place it here. And that's the way you can actually manage your basically your storage, your persistent memory. So we evaluated this idea using these systems. We consider that we have HDD baseline, like the traditional system with volatile DRAM memory and persistent HDD storage. We also, so of course, this has the overhead of operating system and file system code and buffering, as well as also HDD access latency. We also consider NVM baseline, which is exactly the same as HDD baseline, but HDD is replaced with NVM. So that's the good thing is that it still the problem is that we have that operating system and file system overhead, but because of this two-level storage model, but you have faster access compared to HDD. Unfortunately, back then we didn't have, let's say, SSD baseline as well. There should be also flash or SSD baseline here as well, but that's one of the limitations of this work. And persistent memory that we use only NVM and no DRAM to ensure full system persistence. And all data access using loads and stores. So there is no two-level storage model essentially. And it does not waste time on system calls, and data is manipulated directly on the NVM device. So you can see that from going from HDD 2-level to NVM 2-level, we got 24 times speed up, which is quite good because NVM is quite fast. And by going from NVM 2-level to persistent memory, we are getting like 5 times speed up still. So, and that shows also the effectiveness of this idea. I believe flash memory is somewhere around here, if you have it, like because the latency of flash memory, is much better than HDD. Like for example, accessing HDD takes around 10 milliseconds, but accessing read latency of SSD, considering all other latency going on, can be around like 200 microseconds or so, for example. So it is like orders of magnitude faster access by using flash memory. And in terms of energy, also you can observe quite great speed up when we use persistent memory. If you want to learn more, you can also check this paper for more detail. But yeah, so these are like challenge and opportunity that we also discuss here, like the combined memory and storage in a unified interface to all data. And so industry have done work on it. I mean, this slide I have shown multiple times today, but this obtained memory, people actually have shown that how they can add this obtained memory insert it as one of the DIMMs of the system, and you can see that it's actually like DDR DIMMs basically, right? And then they use it as a persistent memory, and people develop libraries that they can use this obtained memory as the persistent memory, and they report result compared to having a DRAM like as a non-persistent memory and a storage SSD as a persistent memory that you have. And people also add processing DRAM engine. I'm not sure why this is here, but yeah. Anyway, so there are many also challenges in persistent memory. One key challenge that I would like to point it out here is that how to ensure consistency of a system data if all memory is persistent. Like there are two extremes, like programmer transparent, let the system handle it. So you don't want programmer, do anything. You want to provide quite program ease. So system should handle it. It's very good for program, but it's very hard to implement, of course. And programmer only that let the programmer handle it. And there are many alternatives in between that I believe actually the good solution probably should be in between. But in research, sometimes it's also good to take extreme actions, because you want to see what are the challenges you're gonna achieve and you're gonna face off, and how you're gonna work on them when you want to push boundaries. And that's why also doing research in emerging memory technologies is quite interesting. So this is an example, like this crash consistency problem, which is actually quite well known. So you want to, for example, add a node to a linked list. So there is a link to next and also a link to the previous node, right? So you always want to do it in an atomic manner, because if you don't do it and a crash happen, then you may get to this kind of linked list that the connection to the previous node is there, but the connection to the next is not there. And then your linked list is not basically is broken essentially. So that's actually a known problem and cause an inconsistent memory state. So there are current solutions that basically explicit interfaces to manage consistency. Essentially, you need to do it in atomic way, essentially. So there are some atomic begin and end that you insert your code here to make sure that all these operations will happen in atomic way. Like either both of them will happen or none of them, essentially. So that's the key that you need to ensure when you are doing it in an atomic way. But of course, it's limit adoption of NVM because you have to rewrite code with clear partition between volatile and non-volatile data, essentially. So that's why this idea, putting the burden to the programmer and compiler is not a good idea. So there are also some code here that I'm not gonna show. You can check it later if you are interested. But essentially, there are some. Let me see. Yeah, so you need to use transactional memory in order to basically make sure that you are doing it in an atomic way. And there are also some lists here that like library access that you need to do it in again transactional memory, such that you make sure that again has been done in an atomic way. But you got the idea basically. So it should be like manual declaration of persistent components. And sometimes you need a new implementation, and also third-party code can be inconsistent state. So you need to put them in a basically transactional memory access. But yeah, so essentially you need to benefit from these libraries and in these codes to provide consistent code. But we wanted to have an approach which like the software transparent consistency in persistent memory, and we wanted to with completely software transparent. So the key idea is that periodically we want to checkpoint the state and to recover to previous checkpoint when crash happens, basically. So there is a new hardware-based checkpointing mechanism that checkpoints at multiple granularities to reduce both checkpointing latency and metadata overhead. And we overlap checkpointing and execution to reduce checkpointing latency. And it adapts to DRAM and NVM characteristics. So we have done a lot of work in this, and that wasn't really easy. And it's not also easy. And I'm not sure if we should actually also recommend people to use it because it adds a lot of complexity to the system, of course. And this, so in this work also, we consider that we have one single node. Like you need to deal with, your memory, your storage, essentially. But assuming that you are thinking of a distributed system and you have data coming from I/O, coming from network, for example, your network card. So how are you going to checkpoint that, And people have looked into also checkpointing in a distributed system, like in a database. But you can assume, how much overhead that can basically that can cause. Like all the checkpointing can cause a lot of also data movement and energy, essentially. So that's why actually finding a solution in the middle between the, completely put it on programmer and completely program transparent is probably the best way to go. But we get very good results. Like our performance was within 5%, 4.9% of an idealized DRAM with zero cost consistency. We have done also work on how we can do overlapping checkpointing and execution, because if you do such things that you run and then spend time to checkpoint and then run and checkpoint, that is quite dumb, right? Because you add a lot of overhead for checkpointing. So the idea is that you want to overlap these checkpointing by running other kernels, other threads, or whatever. So essentially, you should be able to schedule them nicely such that you can overlap checkpointing and execution as much as possible. Yeah, if you want to learn more, you can check this paper. It's going to also be one of the readings in your homework. But there are another key challenge in persistent memory as well, like program ease to exploit persistence. And people have worked on it a lot. You can, if you're interested to learn more, you can check these papers as well. Now we reach to this security and data privacy issue that your colleague actually brought it up. So essentially in NVM, we have these security and privacy issues. So first of all, with endurance problems, we have these wear out attacks. So people actually can design attacks to cause your chip to wear out quickly, for example. So if you, for example, attacker, for example, issue a lot of writes to your PCM main memory, for example, that can cause wear out of that chip. Of course, there are some techniques like wear leveling that people have been using, try to level the number of writes. Like for example, in your PCM, assuming that endurance is 10 to the power 8, and if you write to one cell only 10 to the power 8, then that cell is going to wear out, right? But if you balance your write, you use some technique like a wear leveling that you basically try to write in a balanced way in the whole memory array, then hopefully you can actually tolerate more writes essentially. But when you're designing an attack, attacker can actually be also intelligent enough or creative enough and try to, I don't know, to trick your wear leveling technique such that essentially cause a lot of writes to your cells. So in hybrid memories, you can also have performance attacks. For example, people have worked on it as well. Data the thing that actually your colleague mentioned, that data not erased after power off. So in DRAM, when you just power off your system, your data is cleaned up. Unless you want to do this cold boot attack and you cool your DRAM a lot. But in general, when you power it off, things are done. But things are basically, completely erased. But in non-volatile memory, that's not the case, and you might have some privacy issues here that you need to look into it. So let's conclude. Any questions? I was a bit fast in some slides, but I tried to convey key ideas as much as possible. So hopefully you got the very good insights, some good insights from this lecture. So the future of emerging technologies is bright, regardless of challenges in underlying technology and overlaying problems, requirements. It can enable orders of magnitude of improvements and new applications and compute systems. And yet we have to think across the stack, as we discuss all the time, and design to enabling systems. So here is a very good example. Like you have a new device, this emerging memory technology, and you can design different techniques. Like we have observed, like techniques at microarchitecture, software, and people have done work on algorithm design. Such how you can change your algorithm in order to have less number of writes, for example. So when you design your algorithm, normally you don't consider that at all, right? Like with the DRAM, you never thought, okay, how many writes I have, But with this new angle here, computer scientists also need to be aware that people that they are working on the theoretical computer science, let's say, that these algorithms should be also aware of the number of writes as well, And people have done interesting work in that direction as well. And of course, if in doubt, refer to flash memory, a very doubtful emerging technology that for at least 2 decades. But now you can see that flash memory is, everywhere. In all our pockets. And we're gonna also learn a lot about flash memory next week. There are many research and design opportunities in this area, like enabling completely persistent memory, as we also discussed, computation in or using NVM-based memories, hybrid memory systems, security and privacy issues in persistent memory, reliability and endurance-related problems, virtual memory systems for NVM, and example is virtual block interface. So this is also interesting as a kind of food for thought. The reason that virtual memory has emerged is that basically your main memory was not large enough, and that actually made that was making life for programmer quite hard. The way that they wanted to design programs. So people have developed this brilliant idea of virtual memory that gives illusion of much bigger memory, but using this NVM, you can actually have quite large memory. So like tens of or hundreds of terabytes. So we need to rethink about all these things. Do we really need virtual memory anymore? And all these things are quite interesting to look into. And such topics are quite interesting. When you want to work on emerging memory technologies, in order to overcome the issues, you really need to rethink the whole stack and rethink all the assumptions that you have made decades and decades, and that's quite insightful, and that can, push the boundaries, and you can overcome with many out-of-the-box solutions to the issues. So this virtual block interface is one of the work that we have done also to, think about virtual memory a little bit different. You can check it if you're interested, or you can watch Nastran's talk in one of the computer architecture lecture in fall 2020, 4 years ago. And with that, I'm concluding this lecture. And we are 5 minutes early. Thank you. Questions? We could take that 5-minute break. Okay, then I see you all tomorrow. Have fun.